All right, so if you just watched the video for 5.1.1, I suggest you try pausing and seeing if you can do 5.1.2 on your own. Again, you can see all we're asking to do is construct that probability distribution. So the same thing we did in 5.1.1. All right, so hopefully you paused and are coming back. At least take the time, if you didn't already, do the X's. What are the possible outcomes? So looking here, X is the amount you win in a game. And we can see here, if you get a red card, you win nothing. So it's possible to win nothing, right? Okay, if we keep reading. If you get a spade, you win $5. Okay. For any club, you win 10. Excellent. So you can also win 10 bucks. And an extra 20 if you get the ace of clubs. So here's the only mistake I see on students for this particular problem is an extra 20 means it's getting added to that 10. So this is actually 30 bucks for the last outcome. So once you got your X's down, then you can start thinking about probabilities of those X's. For those of you that don't know a deck of cards really well, do not worry. I don't put questions about decks of cards on the exam because I understand that not everybody knows the deck of card that well. So these are only questions that I'll do in class or in videos. So let's look back at when we win 0 and all these different things. So 0 is if we get a red card. All right, well, those of us who know a deck of cards, half of the deck is red, the hearts and the diamonds. So 2 of the 4 suits or 26 of the 52 cards. I'm just going to go with 1/2. Okay, next, if you get a spade, you win $5. Spades are 1 of the 4 suits, so that's a 1 out of 4 shot. This could also be thought of as 13 of the 52 cards. The last one is the trickiest. For any club, you win $10, but you get an extra 20 for the ace of clubs. So in each suit, there are 13 different cards. So you have the ace of clubs, you have the 1, 2, no, there's no 1, don't listen to me, 2, 3, 4, 5, 6, 7, 8, 9, a 10, a jack, a queen, and a king. So we know that the ace is worth extra money, right? There's 1 of the entire 52 cards in the deck that gives you that extra 20 on top of the 10 for 30 bucks, which means the rest of these, the 12 more, they're the ones that get you 10 bucks, the other 12. So anyways, that's constructing our discrete probability distribution for this problem. All right, and I'm going to go ahead and just continue on with exercise in the next problem, where we're playing now with figuring out what the expected value and standard deviation are. So we have formulas here. I'm going to do this with the formulas, then I'm going to show you the calculator shortcut, which I'm sure you could also see in 5.1.3. So I guess I need that. Expected value is just another way to say mu, which is our mean, remember? So this is how much you would expect to win long term. If you played the game an infinite number of times, the expected value you could take away on average. So this is not how much you would expect to win. If you're playing this game one time, the amount you would expect to win is $0, right? That's the most common thing that's going to happen is winning 0. But this expected value is a long-term, probably like a long-term run, on average, how much people win. So if everyone in the world plays this game, on average, this is how much the game pays out. So expected value, according to this, we are going to do the summation of x px. So our expected value, we're going to take every x, and then we're going to multiply it. There's no multiplication written there, but that's what's happening, with its probability. We're essentially just finding a weighted mean, right? If 0 happens half the time, then let's throw 0 in half the time. If 5 happens a quarter of the time, let's throw 5 in a quarter of the time. So that's all this is just a weighted mean with a formula that you will have available to you on the exam to calculate it. So if I wanted to put this in my calculator, I'm going to do, I wouldn't even bother with the 0 because 0 times anything is 0, but you could type that in. 5 times 1/4 plus 10 times 12 over 52. Oops, that's not times. Ah, where did you go, Webbit? Sometimes I wish I could just click on the screen. Times 12 over 52 plus 30. Oops, I'm trying to move this thing up. Times 1 over 52. I could just divide it by 52. Whatever. You can do this a lot more quickly. So we get 4.1346. Is that right? Yes. All right. So this is the expected value. We should put units on this. Our x, the variable we're talking about, is in dollars. So on average, this game will pay out $4.13 cents, essentially. You do want to keep your extra decimals here. The reason being, if we're talking about averages, this is you want to have those extra decimals for this average. So that's our expected value, $4.13 roughly. So if you're running this game as a person in Vegas and you're actually figuring out how much people should pay for this game, you would want to charge at least $5 to play this game. That way you're netting on average 87 cents every time someone plays. So that's how the expected values are used, mostly by the house, because the house is the one that's going to be there for all of these different people coming in and playing. All right, last piece we need here is the standard deviation. So we got our little sigma here, which is our standard deviation. There are two different formulas available for you to use for the sigma. This formula here has the feeling of the original formula we used for standard deviation, how far everything is from the mean squared and then weighted by its probability. That is the harder formula to do by hand. We could obviously make up a table and do it similar to the ones we did for the Hogwarts example we did for standard deviation in part 2. But this one I think is easier to do by hand. Same exact formula, just easier to do. So that's what I'm going to use. First thing I'm going to do actually is I am going to just do the summation portion. I'm not even going to do the whole thing at once. So I'm going to figure out what the summation of x squared times px is. So this is the exact same thing we just did, right? We did the summation of x times px. The only difference is our x's should be squared. So I'm just going to redo what I did before, but I'm going to square all of my x's. 5 squared times 1/4 plus 10 squared So that's the only difference in that piece of the formula. So if I come back to my calculator, I'm actually going to just do second enter to bring back what I just wrote. And I'm going to insert all of my, oh God, this is not going to be faster with this, but I'm going to insert all those squareds. So, yep, definitely would have at this point been faster to type it in, but it's okay. All right, so 5. Then do second insert, and we'll put the squared in. Come over to the 10. Second insert and put the squared in. And then go to the 30. And insert again a squared. So all that stuff is 46.6346. Okay, so that's only part of the formula, right? We just did this piece of the formula. So let's finish up this formula. Sigma is equal to the square root of that crap we just found, 46.6346, minus our average squared, which, oh, by the way, our average, remember our mu, our mean, is our expected value. So 4.1346 squared. Okay, so I'm going to do all this in my calculator. Square root. I'm going to just throw the answer in there instead of retyping it. Minus 4.1346 squared. 5.4350. Standard deviation, remember, has the exact same units as our mean, which is why we can, in the normal problems, do those little bunny hops. So this is still about dollars. Now the standard deviation gives us an idea of how much spread there is, how much variability. So a game with a high variability is probably better for us if we're a gambler. because we're hoping to win big, right? We're hoping to hit big dollars as opposed to stay there for a long time. Now, if you gamble like I do and you just want to sit there for a long time getting your drinks, then you probably want something that has a lower standard deviation. That way you're able to just kind of stay there and keep winning small amounts. It's fine. So this is our standard deviation, and there's our expected value. You could do these both in the calculator. I'll put that as a second video.